Welcome, folks, to our second day in Chapter 8 and our second lesson about confidence intervals. If you think back to yesterday, you'll remember that every single problem we looked at had a sample size of 40. Well, folks, sample sizes don't have to be 40. In fact, any sample size is allowable. And I'm very glad that we do not have to construct a confidence chart like the one we used yesterday for every possible sample size. Not only would that be time consuming, again, it would be impossible. There is a formula that will generate a confidence interval for us, and that formula is based on the proportion that you find in your sample, right? Your p hat. And to that, we add and subtract a margin of error. And folks, the margin of error is this. It is a critical z. Notice I'm going to put a star by that. That's called a critical z, and that represents the confidence level that we desire. Now, yesterday we had all 95s, but that's certainly not the only possibility. That z star is equal to the desired confidence level, and it can be anything that you pick as the statistician. However, there are some that are used more frequently than others. So desired confidence level. That desired confidence level gets multiplied by the standard error of our statistic, and our statistic has standard error, you'll remember from yesterday, p hat times q hat, that comes from your sample, divided by your sample size, all of that in a square root symbol. Now, if you think about what's going on here, we're going to create the center of our interval will be what proportion we got out of our sample, and then we're including some values on either side of that, again, based on our desired level of confidence. The critical z's that we will talk about most frequently are, for a 90% confidence level, the z-score for that, the z-score that does this, traps 90% of the data inside. That z-score is a positive or negative 1.645. And we've talked about those central intervals before. Well, now we're going to just associate with it the z-score that traps 90% inside. That's positive 1.645 here, negative here. 95%, I hope we're familiar with and remember from yesterday, the z to get that 95% of data inside is positive and negative 1.96. And if you really want to be certain that you're catching the population proportion, you could go for a 99% level, which folks, that's gonna be far out here. Okay, 99% trapped inside. The z-scores that do that are positive and negative 2.576. Again, those are z-scores that we could come up with by looking at central intervals. We have already done it, so I don't see a reason for us to do it again. These intervals will be reasonably accurate if the sample has been randomly selected. That's always going to be important to us. From a binomial, that's a yes or no, a success or fail, a two outcome. So from randomly selected from a binomial population. I'm going to abbreviate there. The second criteria, the thing that will get us a reasonably accurate confidence interval, is we need to have a large enough sample size to assure that both NP and NQ are greater than or equal to 10. Again, that sample size requirement, we want to use large enough samples to guarantee that NP and NQ are both greater than or equal to 10. And finally, the population must be at least 10 times larger than your sample. So greater than or equal to 10n. You want to have a large population and large enough sample sizes to assure that you meet the sample size requirement here, the population requirement here. We mentioned the margin of error, of course, is that part of the formula that follows the plus or minus sign. That is, it is that critical z, I'm going to write the star that way, times the standard error of your sample, which is p hat q hat over n. And so if something were reported as 50% plus or minus 3%, that 3% comes from this thing. That's the margin of error, and a lot of times they use the capital E to stand for that. So let's take a look at a quick example of generating a confidence interval and then interpreting what the results mean. It says we have a sample of 549 randomly selected teenagers aged 13 to 17. That is a sample size right there, folks. That's going to be the N for us. They were asked whether they thought it was okay for parents to put a computer program on their computers or iPads or whatever that limits what teens can get to on the internet. So of these 549 who replied to this poll, 52% said, yep, that's a good thing for parents to do. Folks, we're going to use that 52% as our P hat, okay? That's the proportion in our sample who said yes. That's a success proportion, if you will. That would mean that our Q hat would be the rest of the folks, and that would be 48% or 0.48. I'll write it as a percent here. Of course, when we do math, we're going to use the decimal. It says that we should check the conditions and then make that 90% confidence interval for this situation. Our first criteria is that we be random and binomial, and I'll ask you to look in the paragraph to see if that is the case. It does talk about random, and their answer was either yes or no, so we can check that condition off. We met that. As far as our sample size criteria, 549 times 52% or 0.52 is certainly going to be bigger than 10. As is 549 times 0.48. Both of those will be significantly larger than 10, so our sample size criteria is okay. The last thing we have to do is check the population at large, and as far as teenagers ages 13 to 17 go, I'm pretty sure that there is more than 10 times 549 teenagers that fit that description. So I think we're all good as far as the criteria goes. This is something that should be checked each time, folks, especially, okay, if you are going to be writing the AP test in the spring. They look to know, did you check to see if the procedure you're going to use is called for? And in this case, you have to meet those three criteria, and it is called for here. So we're all good to go. We're asked to find a 90% confidence interval. The critical z that we need, so we've listed all of the other variables. We might as well list this one. We have n, p, and q. The critical z that we need for 90% is that positive and negative 1.645. So now we're all set to build our interval. We're going to center our interval around p hat from our sample, and that was the 0.52. Yep, I put my hats on. 0.52 is the center of our interval. The margin of error that we want at 90% confidence is this, 1.645 times the standard error of our statistic, and folks, that is p hat, 0.52, q hat, 0.48, over sample size, which is 549. I'm going to bring my calculator up and I'm going to enter that in there. You should be doing this on your calculator, so if you would pause that video. Okay, I'm back with an interval, I believe. On the low end of our interval, we're at around 0.48 or 48%. At the high end, we're around 0.56 if we go to 2 places past the decimal, which should be sufficient. So our interval is this, 0.48 to 0.56, and our job now becomes interpreting what that means. We believe that based on our sample, which had this mean, that we have a, in this case, 90% likelihood, since we were going at the 90% confidence level, we have a 90% likelihood of catching the population, the true population proportion of teenagers who believe this inside our interval. We're 90% sure that the population proportion of all teenagers 13 to 17 who think it's okay for their folks to limit what they see on the internet is between 48% and 56%. Now you could also write this as 0.52 plus or minus, and you can see that that would be 4%. Both of those ways of showing the interval are okay, so I'm going to write it that way as well. 52% plus or minus 4%. I generally write the interval in this notation because I'm a math teacher and that's interval notation. However, if we wanted to report with a margin of error, that's what it would look like. All of our confidence intervals need to have a sentence related to the context that explain what the interval means. So I have written a lot of these, and sometimes mine all tend to sound the same. However, what we are saying is we can be 90% confident that the population proportion, or that the proportion or percentage, whichever way you want to say it, of all teens, okay, of all teens in this age group who believe it's okay for parents to limit internet access See, we have to get that context in there. Internet access is between 48 and 55, or 56, sorry, and 56%. Our interpretation is always going to be a sentence. It's always going to address the context of the problem, and it needs to use, folks, statistical language. 90% confident is statistical language, okay? We're saying we're 90% sure. We want to make sure that we reference our interval. We're trying to use it to predict what all teens will say. So the word all or population needs to be in your sentence as well. All right, let's go on and talk just a little bit about some technicalities. You know that if you increase the sample size, you'll generally get a more accurate prediction. That's what the central limit theorem says. However, there is a point of diminishing return, folks. That is a place where your sample size is so large it's not affecting your interval anymore. That margin of error, folks, is affected by sample size. So I'd like to have you think about that. We're going to take that formula, E equals Z star times, and it was P hat, Q hat, over n. And what I'd like us to do is solve that formula for n. If our job is to isolate the variable n, we need to start taking away the stuff that's around it, beginning with the division by z star. So I'm going to divide both sides. E divided by z is equal to, and then we're in the square root, P hat, Q hat over n. The next step would be to square both sides. So I'm going to bring my work up here. When you square a fraction, you square both its top and its bottom. So e squared z squared, sorry, e squared over z squared is equal to, and on the other side we would have p hat, q hat divided by n. Our job is to get n by itself. So the next algebra would say multiply both sides by n, and when you do, you'll have n on the ground floor, is how I like to say it, of this equation. You don't want it in the basement, you want it up here on the ground level. Then we need to get it by itself, and that would be accomplished by dividing by e squared over z squared. Now many of you will remember dividing by a fraction is the same thing as multiplying by its reciprocal. So when I multiply by z squared over e squared, I isolate n, which was my goal. On the other side, I'm going to have this thing, z star squared over e squared multiplying p hat q hat. So if you think about this, folks, if we specify our desired level of error, okay, and our desired confidence level, so I'm going to put confidence level here because we have to have it so that there's only one variable that's unknown. So confidence level is the z that you choose, and we decide how much error we're willing to risk, how much error we'll accept. Folks, if that's true, we can find the sample size that will get our confidence intervals being just like we want them, with a desired confidence level and a acceptable error limit. Now that's pretty powerful. Those of you who will be AP test takers, the AP test includes a formula sheet. However, this is one formula that does not show up on that sheet. So the sample, and there's almost always, every practice test I've ever seen has a question about sample size. This is something that you should memorize. I would also point out to you that p hat and q hat come from a sample. Sometimes, if there's no preliminary p hat, that is, if you don't know exactly what the proportion is, so if there's no known p or p hat, use 50% instead, 0.5 for p and 0.5 for q. If you think about the algebra of that, 0.5 times 0.5 is 0.25, and any other proportion successes, like 0.4 times 0.6 would be 0.24. It's less than what you'll get. If you use this as p hat and q hat, then you generate an interval with a slightly larger, okay, margin of error than perhaps you need. You give yourself a little wiggle room by using 0.5. You do that if you don't have a p hat to use. You don't have some sample data yet. All right, let's see how that works out. Suppose it costs us $5 to survey each person in some sample. You think, okay, p is about 0.5. So we're saying we're not sure, but we think 0.5, and if we use that again, we'll get an interval that is sufficiently large to cover our margin of error. What will our survey cost if you want to be 95% confident and have margin of error around 10%? All right, so I'm going to ask you to think about the formula from a moment ago. E is the 10% that we're seeing here. That's what we'll accept. P is equal to 0.5, or you could call it p hat, but really this isn't from a sample, so p is more appropriate. Q is 0.5. 95%, the z, the critical z that gets us a 95% is 1.96. So here comes our formula. The sample size that we need to get, because if we're going to talk about cost, we got to know how many people we're asking. So we're going to find the sample size and use that to answer the question. Okay, so it was z squared, so 1.96 squared, over error squared, margin of error, 0.10 squared, multiplied by p hat times q hat, so 0.5 times 0.5, which we've already said is 0.25. I'm going to go ahead and put that into my calculator. I'm going to round my interval to the next highest whole person, because you wouldn't want to cut a person in half, and you don't want to round down when it's a person, you want to round up. So let's see, I'm going to have 1.96 squared divided by 0.1 squared, all of that multiplying 0.5 times 0.5, which I already know is 0.25, but I'm going to put it in just like I would if I didn't have that advanced knowledge. This fraction divided by, and folks, your calculator will do the division correctly. You don't need to put parentheses around this, although you could if you wanted to. It won't change anything. According to that, we need to sample about 97 people. Okay, we need to have a 97 as our sample size, and what our survey will cost then is that 97 times $5 per, and 97 times 5 is about $485. Okay, that sample size formula is a good one to recall. Again, good one to remember. If you wanted to have less margin for error, okay, if you were not willing to accept 10%, what do you think? Would you need to sample more or fewer people? So if we're going to cut this down, that means that that fraction, let's see, if we divide by a smaller number, that means that we get a larger value here. I think if we want to have less margin of error, our sample size would have to be larger. And if you think about the logic of that, it would make sense anyway without the mathematical explanation. If we want to have less wiggle room, we need to ask more people. Okay? Try it. It says, suppose we want to have a 5% margin. So if we want to change our computation then to be sample size is, and I'm going to write this the efficient way, 1.96 over 0.05 squared times point, and we already know it's 0.25. Sure enough, to get that extra 5% that we wanted, we've got to ask a bunch more people, really. According to this, we'd need to have around 385 people, which would cost significantly more if you think about that. At $5 per, that would bring our cost up to around $1,900. Ladies and gentlemen, I would like to have the more sureness, okay? But my practical side says, will I accept a little less surety for a lot less money? Okay, you think about it. You're going to be the business person someday. If there is an estimate for P, you can use it instead of the 0.5, and that should, folks, decrease the sample size. All right, that's all I have to say today. I'm going to ask you to get out there and try that. You try at your earliest convenience.